Everybody, we're going to begin the afternoon session. Let me just tell you what we're going to do is I'm going to go through a couple of presentations, and then we're going to start playing with some software. We are not going to analyze the data we took last week today, but we'll analyze it tomorrow. I was just in communication with the people at Goddard, and they said that they had analyzed it. Early before lunch they hadn't, but they had analyzed it, and I want to take a look at it, and then we'll work on it together tomorrow. This morning, Jean-Pierre talked a lot about interferometry and how we derive the delay and stuff. And this afternoon, I'm going to talk a little bit start off by talking about how we model the delay and some properties of the delay. And the delay is important because that is our observable. It's our primary thing that we get all the other information from. So one thing to always bear in mind is units. When we measure the delay, we measure it to a precision of picoseconds. Who knows what a picosecond is? 10 to the minus 12 seconds, yeah. So if I have 10 picoseconds, which is sort of a normal unit, that corresponds to 3 millimeters. And when we measure the delay, for our current systems, the SX systems, the uncertainty in the delay is about 20 or 30 picoseconds. So it's right like that. In the new system, it's about 4 picoseconds. So it's much smaller than that. And sometimes people will give the delay in terms of picoseconds, and sometimes they'll give it in terms of millimeters. And the conversion factor is just the speed of light. So it just depends on what you're talking about. Since ultimately what we're dealing with is position measurements, oftentimes it's easier to think about it in millimeters. So here is a picture you have seen, I don't know, probably 5 times so far. And this shows the schematic diagram, and we have the geometric delay. I call it the geometric delay. And this is just that one side of the triangle there. And this is how you can give it in terms of a formula. It's the dot product of the vector to the unit vector to the source, dotted in to the baseline vector, R1, Ri minus Rj divided by C. So I have a question for you, and I'm going to give you about 3 minutes to think about it. Here's a picture of the Earth. What is the maximum delay we can measure? I'll tell you that the first time people asked me this, I said, oh, it's obvious. And then I gave the wrong answer. In Earth. Suppose I had 2 stations on the Earth anywhere.
Diameter of Earth, right?
That's what I said, but that's wrong.
What was his answer?
It was wrong.
But no, what he said, I don't know.
He said the diameter of the Earth. Anybody else have anything else to say? So let's suppose, how would it be the diameter of the Earth? Suppose I'm looking at some source out here. Okay? I have a source out here. To have the diameter of the Earth, I'd have to have one antenna here.
It's not
Not showing.
The cursor is not showing that.
Oh, the cursor is not showing that. Okay. So.
The pointer.
Does this work? Yeah. Okay, so I have a source out there. And if I wanted to have it, suppose I had a station up there and a station down there, then the delay is going to be 0 because it's going to hit both of them, right, at the same time. So the only way I could have it diameter of the Earth is if I had a station there and a station there. What's the problem with that?
One will look and the other will be blind.
You can't see through. You can't see through the Earth. Yeah, the Earth is optically dense.
Wow.
So here's the answer. So you can see that, you know, this plane wave starts out here, it hits there, and then it hits there. So the maximum delay you can have is 1/2 is the radius of the Earth. Yeah. And if you do the arithmetic, this corresponds to about 0.02 seconds. So that's the largest delay that you can get.
Because the 90 degrees right?
Yeah. Anyway, so you have the radius of the Earth is 6,000 kilometers divided by the speed of light. So here is another question. Suppose I had a network with 3 stations at 1, 2, and 3. Now, I can measure the delay on each of these baselines. So I can measure the delay from 1 to 2, I can measure the delay from 2 to 3, and I can measure the delay from 3 to 1. So my question is, I'll call that the triangle delay, because it's delay going all the way around the triangle. Yes? No. So my question is here, is that I have this triangle here, and I'm measuring delay, all the delay. So I measured the delay from 1 to 2, from 2 to 3, and then from 3 to 1. So I give that formula up there. What is that equal to? What is a combination? What does it equal? Okay, let's see what it equals. I'm going to use the formula for the delay right here. So I have R1 minus R2, R2 minus R3. Oh, and this should be wrong. This should be R3 minus R1. And when I do that, that's going to sum to 0.
One second, teacher. Your computer. Let's try connect my.
Okay, I'm going to go back and fix this thing quickly.
Let's use my hotspot.
Go ahead.
Okay. Let's try again.
Okay, going back to this slide here. So if I go all the way around the triangle, I find out that the delay should be 0. And a couple of comments I have is that when I measure the delay, each measurement has some noise in it. So if I actually add up all of these numbers, they're not going to be 0, but they should be close to 0. So, this is one check that your stuff is working okay. How many of you guys have taken a course in statistics? Nobody's taken a course in statistics. So then what I'm going to tell you is going to be new to you, but maybe you can use it later on. So I have some variable, A, and I make measurements of it. And I have a true value over there, plus some noise term. And the noise term is just random error. And the question is, what is the value of A? And I'm going to assume that that these random errors have an equal probability of being plus or minus, that if I add up a bunch of them, it's going to average out to 0. So I say that A has an uncertainty, sigma A, of 1 over n, and I take this random variable and I square it. And this is just another way of writing that same thing. So it's basically a measure of the size of that variable there. So it's not the average size, but I square it, I sum them all up, and then I take the average. So this is called the sigma. In this context, it's also called the RMS error. And if I have suppose now I say f is, I multiply f times this, I have f be a function of a scalar value times a, then what is the uncertainty of f? Then the uncertainty of f is just going to be a times the uncertainty of that scalar value. Times the uncertainty of the original random variable. And I just go through the proof here to show it like that. This is important because a lot of times what we're dealing with is we're dealing with something that is a function of several random variables. And so we want to be able to say, what is the uncertainty in this function? I know it's composed of lots of different parts, and each part has some error. What is the uncertainty of the whole thing? So here I say, suppose I have 2 random variables. What is the uncertainty of the sum of them? Does anybody have a guess what this should be? Just tell me something that sounds reasonable.
It's going to be bigger than A plus B.
Going to be bigger than A plus B. Actually, it's going to be smaller. So here is the answer. It's going to be that whole thing there. This is the uncertainty from the first term. That's the uncertainty from the second term. And then I have this other term here, and that has to do with if A and B are not independent. That if when A varies, there's some error in A, there's also an error in B. But if I don't have that term there, then it's just sigma squared A plus sigma squared B. And if A and B are the same, then that's just going to be square root of 2 times sigma squared A, which is less than sigma A plus sigma B. So why is this? Well, sometimes I can have the error in A be plus and the error in B be minus, so they cancel out sometimes. And here I just go through the proof of this, which if you haven't had statistics, I'm not going to bore you with it. But I just go through the definition. So I'm going to use this to go back to our first thing about what is the expected closure error to go around this triangle. And I'm assuming that the measurements are independent. And in that case, this closure error is this the error for baseline 1, 2, the error for baseline 2, 3, the error for baseline 3, 1. You know, and I have a square here and I have a square there, just because it's easier to look at that. And I put in typical values for the baseline error is about 30 picoseconds, so I have 3 times that. So this is about 50 picoseconds squared. So if I compute the closure, I would expect that I'd see things which are sort of on that magnitude. If I have something that's much bigger than that, then there's probably a problem with some station or one of the baselines. And if I just have 3 of these, I can't figure out which one it is. But if I have a lot of triangles, I might be able to figure out what it is. You know, for example, here I have something where I have 4 stations, 1, 2, 3, 4, and I have lots of different triangles. So I have this triangle here, I have this triangle there, I have that triangle there. And if I find that all the triangles that have that station are bad, then there's probably something bad with that station. So that's just something that you can do. Now, what I'm going to start talking about is modeling the geometric delay, or modeling the delay. And you know, here is just this formula that we've seen a lot of times as this is the delay there, this top line, and I put in this omega here. And this omega is just a rotation matrix. And it's a rotation matrix that rotates the Earth frame into the space frame. But for most of what we're doing, it doesn't really, we don't need to talk about that. So this is what we're interested in, but here's what is actually measured. And this is what comes out of the correlator. And there's the geometric delay, plus there's all of these various kinds of terms. There's a clock term, an atmosphere term, a cable term, an ionosphere term, a gravity term, blah, 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 blah. And so we need to either calibrate these other terms or estimate them in order to get the geometric delay. So the simplest thing to think about is the clock term. Now, at each site there is a hydrogen maser, which is an atomic clock which is very, very precise. And ideally, the clocks would be synced with each other, but they're not. I'll tell you that at the hotel I'm staying at right now, they have clocks everywhere. And one of the clocks is 10 minutes off. And it drives me crazy. Because it's a clock right where I have my breakfast. And if I look at that, I'm going to be late coming to the class. So if the 2 hydrogen masers have an offset between them, that's going to go into the measured delay. And it's just going to be whatever that offset is between them. Does this make sense to people? But this is something that you can solve for because this is going to be constant for all of your measurements. The other things that you do are going to vary depending on what source you look at. You know, if I look at this source or that source, then the delay is going to change. But that piece there is going to always be the same. So I should be able to estimate that. Now, besides clocks being off, what else can happen with a clock?
2 p.m. 32 minutes.
No, okay, so instead of a clock just being a constant off, one thing that can happen is the clock can run fast, and that it can, say, gain a minute every day. You know, so today it's 1 minute off, tomorrow it's 2 minutes off, etc. So there's some rate in it. So that, you know, the hydrogen masers have something, they keep track of a frequency, and they try to adjust the frequency, but the frequency can change. And if you have that, then what you end up happening is the clock is off and it varies with time. And the simplest thing is that the variation is a straight line. And in that case, what I do then is I have a term where I have the offset, and then I have this clock rate term. So here I just have a straight line for the variation in the clocks. So one comment I have here is that I don't know which of these hydrogen masers has a problem. It could be maser 1 or it could be maser 2. And in general, if I have a network with like 5 stations, I'm going to have you know, lots of offsets, and I can't tell which maser is good and which maser is bad. So what you do is you say, I'm going to assume this maser is perfect, and then reference everything else to it. And yeah, and usually if it's a good choice, what you'll find is that your clock rates will be good for everything. If you find that all the clock rates are large, then that means you've chosen a reference station where the clock is varying. Does that make sense? Okay. So here's a simple thing where I say, I have a clock offset and I have a clock rate. But maybe things are more complicated than this. And so you may want to say, I'm going to have some more complicated function. So, and I just put that up here by f of t. So one thing here is I can say, I'm going to add in higher order terms. So I'm going to have a clock offset, plus I'm going to have a clock rate, plus I'm going to have an acceleration. So I have some sort of polynomial here. Or another thing I can do is I can have a clock offset and a clock rate, and then I can add in harmonic terms, like a times cosine of the time and b times sine of the times. And one rationale for this is that sometimes the hydrogen masers, their behavior is temperature dependent. So it depends on how hot and cold it is. So you may have variation over the day as things get hotter and colder. And you could have this as complicated as you want to do. Generally, rather than do it like any of these things here, the modern way of doing it is you parameterize it as a piecewise linear function. So you assume that it has some value here, then moves at a constant rate to another value, then it moves at a constant rate to another value. And this is what the clock at one of our stations estimated looks like. It has some overall things, but if you look at each piece there, the rate is constant for some period, for that period of time. And generally for clocks are pretty stable. So usually we estimate a constant rate for every hour. So, you know, this is how we estimate our station clocks. And those lines there show us the uncertainty in our estimate of the clock position over time. Okay? Everybody understand what we're doing here? Kind of.
Picoseconds, teacher, the variation.
Yeah, the variation is, here it's, you know, picoseconds. So it goes, I don't know, 0 to, I'm not sure. Anyway, plus or minus 100 picoseconds over the span of this. But during any given time, the variation is smooth. Yes?
How do I know how much wrong clock is? Because if I am here in Fortaleza and I say, okay, now is 2 a.m. and
So there's a whole thing about clock synchronization.
Yes.
And one of the things that we do at the beginning of all our sessions, try to align our clocks as well as possible, is the GPS antennas, GPS satellites broadcast a time. So we look at that time that GPS satellites broadcast, and we use that. And if you want to be extra careful about it, you also take into account how long it takes for the signal to get from the satellite to where you are. There's a whole area of science about time transfer, how to get precise time transfer.
And you have to assume that the light, velocity of the light is the same when you're going and when you're coming back, right? Because
That's true. But all you want is something that gets you close enough, and then you solve for the rest of it. So the next thing I'm going to talk about is atmospheric delay. And this is caused by delay as the light signal travels through the atmosphere. And there's two parts of this. One is that, as light goes through a medium, anything goes through water or air, it's slowed down.
Because they change the reflections, right?
Because the index of refraction, it's slowed down by the index of refraction. And roughly speaking, the denser the stuff is, the slower the light goes. But that's sort of half right. But the other thing that happens is the signal path changes. So that's also going to change propagation. So the simplest example is I assume that I have an atmosphere and it has some constant density and the path goes straight like that. Now, the length of this path here is 1 over sine elevation compared to just going straight up. So as I go further and further down, this path length increases. So it goes through more and more of the atmosphere as I go down to lower elevations. So the atmosphere delay should be equal to the height of the atmosphere times some constant A there. So the important parts here are, roughly it goes like 1 over sine L, so that at lower elevations it gets much bigger, and at higher elevations it gets much less. Now, as I said, this is complicated by the fact that I also have some bending like that. And so what people say is, rather than have some simple sine over L thing, they're going to have some mapping function. They're going to say that the atmospheric delay there is equal to some number there, and then this thing they call a mapping function. And the mapping function just says, if I'm pointing at this direction, how much delay do I see? And the mapping function depends on the elevation. It also depends on the temperature and the pressure of the atmosphere. Ultimately, it depends on the index of refraction. And there are lots and lots of different kinds of mapping functions that people have used. And here is just a chart that shows, here's a chart that shows, let me back. So this part here, the zenith delay, that's the delay if I'm looking straight up. And that just depends on the properties of the atmosphere. And you should be able to calculate that if you know the the atmosphere. Mostly it should depend on the pressure of the atmosphere, because the pressure tells you, tell me, what does the pressure tell you?
How much is forcing
That's right. It's how much atmosphere is above you, what the weight of the atmosphere is. So that should be the most important thing. And so there are, some formulas for what this delay is. And here's a formula here, and it has a term that depends on the pressure, but this also has a term that depends on the temperature. Here's another thing here. This is a formula that we use, and it mostly depends on the pressure term. There's also a term here that depends on the height of the station and the latitude. The latitude is like, do you know what latitude is on the globe? And the rationale there is that the Earth's atmosphere is not uniform. The Earth is an ellipse, and that sort of takes into account the fact that it's an ellipse. So that's a model that we use, the Sastamonian. But there's some others there. So there's probably about 15 or so of these, and at various times people have tried to come up with better ones. So that's like one part of the atmospheric delay. The other part is the mapping function. And here's a picture of what the mapping functions look like. And the standard form is to have this sort of continuous fraction sort of thing, where you have 1 over sine of the elevation plus other stuff. And sometimes you have sine of elevation, sometimes you have tangents. You have these constants here. And these are these parameters A and B. And these parameters A and B sometimes are fixed values, and sometimes they depend on the temperature or pressure or things like that, or the site location. The mapping function that we used to use was this one, the Neal hydrostatic mapping function. And this is something that Arthur Neal invented back about 30 years ago. And what Arthur did was he sent up weather balloons, and the weather balloons rose into the atmosphere, and they measured the temperature and the pressure and the humidity as they went up. And so he did this at lots and lots of sites, and then from that you can get a profile of the atmosphere, and you can figure out what this mapping function should look like. So that's the one that used to be pretty standard. Now, things are a little more complicated than this because we have water vapor. And water vapor does not mix in well with the atmosphere. And you can see that because you see clouds. Clouds are just, sort of condensed water vapor. And you also have that the water vapor tends to be lower down. So you have the water vapor is, I'm not sure, 10,000 feet or something. You don't see much water vapor above 10,000 feet. But then you still have plenty of atmosphere above that. So people have not one mapping function, but two. You have a part for the, we call it the hydrostatic delay, or people usually call this the dry delay. Then you have this other mapping function for the water vapor. And people usually call this the wet delay because it has water in it. This part here can be well determined from local measurements. This thing here has to be determined empirically. You have to estimate it. So, how do we go about estimating it? Well, we do exactly the same trick we did with clocks. Oh, let me go. So this is just something where I talk about different kinds of mapping functions we have. Neal mapping function used to be the standard. Then back around 2000, some people in Vienna came up with a better mapping function. And what they do is they use numerical weather models. Does anybody know what these things are? So people have these big models of the atmosphere, and they have the temperature and the pressure on this big grid, that covers the whole world. And they use this to predict what the weather is going to be. So that's a primary purpose. But given these models, you can also get information about what's in the atmosphere. So, people take these models and then they figure out what the mapping function and what the delay should be based on these models. So this Vienna mapping function gives an empirical mapping function derived from these numerical weather models every 6 hours. So there's a new mapping function every 6 hours, and between those you'd have to do some kind of interpolation. And this information is available at a website from the Technical University of Vienna. About 5 or 6 years ago, they came up with an improved version called VMF3, Vienna Mapping Function 3. And what we do is we use VMF1 if it's available, otherwise we use VMF3. Okay. So how do we estimate the wet atmosphere? Well, we're going to use exactly the same techniques as we did for clocks. We're going to assume that the wet atmosphere is some function times the wet mapping function. And this function here can be anything we think is reasonable. It can be a constant. It can be an offset. It can be an offset and a rate. So the same sort of things we did with the clocks. But as I said, nowadays what people do is they estimate a piecewise linear function. And here you can see what the zenith delay looks like as a piecewise linear function. And you can see the variation here is much larger. It goes plus 300 picoseconds down to minus 200 picoseconds. So a large variation. And this is amplified. So this is what the delay is when you're looking at the zenith. If you're looking at an angle, it's much larger. So this is an important source of error. And in any case, that's what the atmosphere mapping function looks like. The next thing I'm going to talk about is ionosphere correction. When the delay signal is passing through the ionosphere causes a signal to slow down. And the amount of slowdown depends on the electron content, how many free electrons there are in the atmosphere. And here is the formula for it. So I have the measured delay equals the true delay, plus there's this thing that goes like 1 over f squared. And here's a chart that shows the ionosphere correction. And you can see that this dies off very quickly. So one moral from this is that if you observed at higher frequencies, the ionosphere correction is going to be less. Now, here I just show it for a single frequency, but actually you can measure this at 2 frequencies. And this is what we do. We measure it at X band and at S band. So X band is at 8 gigahertz and S band is at 2 gigahertz. And we have this thing where we have 2 equations and 2 unknowns. We have these 2 measured quantities there. We have this delay that we want to find. And we also have the TEC, the total electron content. And so we can use this to find T true and the TEC. And this is exactly the same technique that's used in GPS. In GPS, to calibrate the signal, they have broadcasted 2 signals, and they make a combination. So here, I'm going to call the true delay, this is the ionosphere delay, This is found by, it's this particular combination. This doesn't have any ionosphere in it. And I can rewrite it in a couple of ways. I can rewrite it in this way, so it's a sum of the X-band delay and the S-band delay, or I can also write it in this way here. And in this way I have the X-band delay, and then I have some correction term there. So this is the ionosphere correction. So one question I have is, of these terms here, Tx or Ts, which one is bigger? Why?
The band is bigger.
Yeah, I mean, if I do the calculation here, I have about 64 over 60 down there. I mean, that's what, so this thing is much bigger. And this term is much smaller. It's a factor of like 16 smaller. The other thing I can do is I can say, I have this ionosphere delay, and but it's a function of the X-band and the S-band delay. And both the X and the S-band delay have some kind of measurement error in them. So then the question is, what is my measurement error of this combined product? And using the stuff that we did earlier, this should be a plus sign there. Here is what the ionosphere delay measurement error is. So I have a contribution from X-band, I have a contribution from S-band, but the largest contribution is from the X-band because of that factor there, the FFX squared over that. This factor there is about a 15th, that first one. So one lesson to this is that errors in S-band are not as important as errors in X-band. Suppose that I don't have measurements of two bands. You know, what can I do? My data is going to be corrupted. Now, one thing you can do is you can get the ionosphere from someplace else. And the place you can get it is from GPS. As I said, GPS uses exactly the same technique. And the GPS guys have lots and lots of receivers. And because of that, they can make models of what the ionosphere is all over the globe. So to use it in VLBI, what you need to do is you need to figure out, I'm here, my ray signal is going to go through the atmosphere up here. I get the value of the ionosphere correction up there from GPS. And then I have to multiply this by some mapping function. And I have the same sort of thing in that the lower down I am, the longest path is through the ionosphere, so that makes it larger. So here's a chart that I downloaded just this morning when I was preparing this. And this shows what the ionosphere is, was at 0 hours UTC this morning. So 0 hours UTC is at 3 o'clock in the morning here. So you can see that there's a lot of stuff over the equator, generally speaking, and then as you get towards the pole, there's not as many things. There's stuff over here and stuff over here, and mostly that's because that is where the daylight is. So where the daylight is, where the sun illuminates, you have more TEC. So TEC, as I said, stands for total electron content. It stands for the free electrons in the ionosphere. And let's see. How do I get this to go? Come on.
I think it should be nighttime. Local time, right? So we need to see if it's 9. It's 3 ahead.
Yeah. So it's 0.
PM, yes.
Yeah.
Excuse me, teacher.
Okay,
Left, right.
how do I do this?
You need to another point. Look here.
Okay, so there's a chart showing how the TEC varies over time. So this information is available from JPL. Other people do this as well. I'm going to close this section by talking about building the normal equations. And, you know, it looks pretty complicated, but actually it's pretty simple. And for each observation, for each measurement observation, we need to construct the following things. We need to construct this O minus C vector. This is the observed minus the calculated vector. And then we need to calculate the partial vector. And the partial is how much the delay, partial derivative of the delay with respect to whatever parameters we're interested in measuring. And this is, I like to view this as just a vector, and the number of components are the number of parameters we're estimating. So if we're estimating 10 parameters, then this has dimension 10. Then we update the normal equation by adding this new term here, where we take this vector and we multiply it by its transpose, and then we divide it by the sigma squared. And the sigma squared is because of the uncertainty in the observations. So this is just very easy function to do. You know, we just have this this vector, and we multiply the components out. And we're adding in, on a 10 by 10 matrix, we're adding in all these components. And then we're also updating the B vector by a similar sort of thing. We have this F vector, and then we multiply it by the O minus C, and that gives us a new B vector. So we sum over all of our observations, and at the end of this, we invert, and we get our estimated parameters A. So, you know, that's how we do it. If you look at the equations, it looks pretty complicated. But if you think about it in this way, I find that it's much easier. So let's look at a simple example. And our example is, I'm going to look at a session where all I want to estimate is UT1. That's really what I'm interested in. But I have to estimate other parameters because they're going to corrupt the delay. So my first parameter is going to be UT1. My second is I have to estimate some kind of stuff for the clock. So I'm going to assume a clock and a clock rate at Wetzel. So that's going to be my model, is a clock and a clock rate at Wetzel. And then I'm going to assume an atmosphere and an atmosphere rate at both Wetzel and at Coquet. So here's what the delay looks like. Here's that delta UT1, that's the parameter I'm interested in, and that's the partial. Here is my clock offset term and my clock rate term. I multiplied that by delta T. Here is my atmosphere term at Wetzel, the offset and the rate, and there's a mapping function. And I have the same sort of thing at Coquet, the atmosphere and the rate. So I think do people sort of understand where I'm getting this from? So from that, I can just read off what the partials are. So for any observation, for my F vector, these are just the parameters. So this is the UT1 partial. These terms here are for the clock. These terms here are for the atmospheric Wetzel. And these terms here are for the atmospheric Coquet. So easy to do. So I can just step through. For an intensive, I have on the order of 20 or 30 observations. I could almost do that by hand. If I have a 24-hour session, I have a lot more parameters. And so I'm going to just work through the parameters I have here. I have, usually I estimate EOP, I have 3 components. I have UT1, I have X pole and Y pole, and I estimate a rate for each of them. And then I estimate nutation, and that's 2 nutation parameters. So that gives me 8 parameters. Now I'm going to model the atmosphere, and I'm assume that the atmosphere is a piecewise linear function that has rate breaks every 20 minutes. So it can go up and then change, and then up and down, etc. But I have 72 different pieces of the atmosphere. I'm also going to estimate something called gradients, which I realized I hadn't talked about. A previous model of the atmosphere assumed that things were azimuthally symmetric, so things looked the same 360 degrees. But in reality, if I look over there and I look over there, the atmosphere can look different. And gradients account for that. So I'm going to put in gradients, and then I'm going to also estimate clocks at 1 hour. And if I look at this for a 10-station session, I end up having 1,000 parameters. So I'm going to be estimating 1,000 parameters. And that starts to get hard to do by hand. So it's a good thing we have computers. Now, one of the things I'm estimating, the parameters that are, most of the parameters I'm estimating are the clocks and the atmospheres. And how I model them makes a big difference in how I set up things. And there's one way of doing it. What we used to do was we'd say the clocks, the atmosphere starts off over here, then it goes up like this with some rate. And then over here the rate changes, and then over here the rate changes, and over here the rate changes. And in the second epoch, we say the rate is just the first rate plus some delta to that. And then this next thing we have, well, the rate is the sum of the 2 previous rates plus another rate. So we end up having like 25 or 24 rates, then this offset. So it gets very complicated. But there's an easier way of doing it, or a better way of doing this. And this is to model the atmosphere as a sum of a rate term, which is this thing here, then plus these hat functions. So these hat functions go from 0 up to 1, and then down to 0 again. And you can show that you can model any piecewise linear function as the sum of these terms. Now, one of the nice things about this is that if I look at any interval here, the only derivatives that are non-zero are a few of them. In this interval from 0 to 2, the only functions that are non-zero are this rate function, which is non-zero for everything, and then this first hat function and this second hat function. Do you see that? Because those are the only stuff that's colored here. And similarly, if I go over to 2, anyway, as I keep on going, at the most I have 3 of these functions are non-zero at any time. So what that means when I'm computing this F vector is that rather than have 1,000 things that are non-zero, I only have 24 components that are non-zero. So that makes adding it to the normal equation is easier. And it also means that there are tricks you can do to solve the normal equations. Okay. I want to do one other presentation, and then we'll break. And then after that, after the break, we'll do some software.
Okay.
So can you help me get the other presentation up?
Okay.
Are there any questions online? Is anybody keeping track of that? Just pull up the other presentation. Actually, it's okay. What do I do here?
Okay, you want to, let's presentation.
So this covers some of the same material that I just did right now, and it also is a recap of a presentation last week. Last week I gave Dan McMillan's take on modeling the modeling delay. This time I'm going to give Lucia, and I think Lucia's is actually a little better organized, which is why I wanted to go through it. Okay, so I just have to do it this way. So here's our summary. Geometric principles, relativistic delay models, final message. So we've seen this picture before. Just a variation of it. We have our delay there given in terms of that dot product at the bottom. Yes.
If you select that, it is in full size.
Full size, okay. Okay, so we're familiar with this. And one of the things that Lucia does is we're going to consider the delay to the center of the Earth. And this is the delay that's used in computations. And in VLBI analysis, we talked about this. What we have is this observed delay, and then we have the delay which is corrected for instrumental delays, and then we have the observed minus the calculated, and then we do some sort of adjustment. So that's the big picture. And we have to do a lot of transformations from one coordinate system to another. We transform from the celestial reference frame to the celestial to terrestrial reference frame. Some of this is Lorentz transformations. We have the Earth is moving around the sun, so that's a correction we have to make. The Earth is moving around the galaxy, so that's a correction we have to make. And a lot of this is happening in the background. Now, one of the places that tells you how to make these corrections, or what the best models is, the IERS conventions. IERS stands for International Earth Rotation Service. And every year, or every several years, they update all the models, the best models. Every year or 2 years, there is something called the United Analysis Workshop. And this has people from VLBI and GPS and SOR all coming together, and they spend 2 or 3 days talking about the models they use and talking about improvements to the models. And based on discussions there, the conventions get updated. And the key idea here is that all of the space techniques should use the same models, because this allows you to compare the results from one technique to another. If the techniques use different models, then, and you see differences between the techniques, you don't know if it's a real difference or if it's just the fact that they're using different models. So, one of the first corrections is a correction for general relativity. And this has to do with the correction due to bending of space. And here is a formula. You know, this big thing here is called the consensus model. There was a convention in Washington, D.C. in about 1995 where they had several smart people come together, and they came up with this simplified version of what the delay is. Now, this is a schematic showing the sort of different things that the steps you are going to go through. Is first off, you do start off with the International Terrestrial Reference System, and you apply station corrections to that. Then you do a transformation to get it into the Geocentric Celestial Reference System. Then you do a Lorentz transformation, et cetera, et cetera. And you end up with like all of these terms here. And you know, this is, you've seen this formula before. This is like the measured delay, and then those are the observed measured delay, and then these are the various terms that you want. This is the geometric delay, clock, instrumental, blah, 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 blah. So here's the first thing, is applying station corrections. This is things like loading or linear velocity or other things. And later on, so the first thing here is you model a station as evolving linearly. Now, we actually have, for places where there are earthquakes, we have a more complicated model there. But then you have other corrections too. And here are the list of a bunch of the other corrections. So solid Earth tide, we talked about that. When the moon is above, the Earth expands. This is like a 40 centimeter effect. Rotational deformation, et cetera, et cetera. You know, here's a plot showing the solid Earth tides, the variation over a month. You see plus and minus 20 centimeters, depending. And I think this plots the U, E, and N. So it not only the up, but the east and north components. Now, one of the effects you have is ocean loading. And in ocean loading, what you have is, if you have a bunch of water, it's going to cause the land to go down. And so you see that loading correction there. And ocean loading is larger at stations which are either island stations or near the shore. So here's Koke, which is an island in the Pacific. Here is Wetzel, which is a station which is in Europe. So the ocean loading contribution here is small. Now, Fortaleza is near the coast, so the ocean loading contribution here should be big. Atmosphere loading is exactly the same thing, but in case instead of the atmosphere, in case of the ocean, we have the atmosphere. So, just want to brag that I and Dan McMillan were the first people to show that you could see the effect of atmosphere loading in VLBI data. We wrote a paper in like 1992 to show that VLBI data was affected by this. Before that, people knew it was a theoretical thing, but they didn't know if you could actually see it. Pole tide loading. This has to do with the rotation of the pole and the variation of the pole. And this is a small effect, a couple of millimeters. Hydrology loading. I talked about this. You have a bunch of water someplace, like in the Amazon or in the Three Rivers Gorge Dam in China. And here is a chart that just demonstrates schematically the size of these different effects. So the largest is the tidal effects, and then ocean loading, and then these things are smaller. There are two kinds of delay of corrections associated with the antenna. One is thermal expansion, and one is gravitational deformation. And there are tables that tell you how to calculate these depending on what antenna you have. We have models for the thermal expansion. We have models for all the antennas. Yes?
The age of the antenna affects the gravitational deformation. Because if you have an old antenna, by the time the antenna exists, it's going to deformate more and more and more.
It might. It might. You're saying just like an old person? Say.
Yeah, because the material is going to accommodate in the new position.
Maybe. I hadn't thought about that. It's a possibility. Anyway, so here's a chart showing gravitational deformation. One of the problems we have is that we only have gravitational deformation models has to be surveyed. So you have to send somebody out there and have the antenna look at different places and see how the antenna changes. And it's not an expensive job. It's about $30,000 to do it. But we've only done it for about 12 antennas. And we have 40 antennas. And so that's an effect that we know causes error, but we just haven't done it. And generally that's going to be, in effect, it's going to be larger for big antennas than small antennas. For the Vigos antennas, the size should be on the order of a millimeter or two. So here's a chart showing the various kinds of contributions we have. One of the things that Lucia does here is she plots up the atmosphere loading here. So this gives you sort of a good idea for what the total effect, not atmosphere loading, but just the troposphere. How much variation you can see there. Okay, so previously everything we were talking about was the Earth. Now we're going to do this rotation where we get into the celestial reference frame. We're starting with an Earth fixed frame. Now we're going to rotate that so that we're in the same reference system as the stars. And you just have this rotation matrix here. It has actually 3 rotation matrices. And we perform a Lorentz transformation not going to go into this. And here's this thing where we were talking about gravitational deformation, that when you are near a star, the path bends, as opposed to if you're further away. And so that's going to cause a change in the path length with respect to each other. And that's where you have this consensus model come in. So
Teacher, because the deformation like Hubble.
yeah. Anyway, I mean, here's a chart showing the gravitational deformation for Jupiter and from the Sun. You would think that the deformation, the gravitational delay from, Jupiter and Saturn. Jupiter is bigger, which is the reason that this effect is larger. You have the same sort of thing with the Sun, but generally you don't see it. And the reason you don't see it is because we don't observe close to the Sun. And we don't observe close to the Sun is because if you do, you're going to fry your electronics. And here's this famous consensus model. They are coming up with this model is supposed to be good at the 1 to 2 picosecond level. They're coming up with a model which is good to better than that, which will probably be used, I don't know, next year or something like that. And then this is what we were talking about is the delay model. How do I model the clocks and the instruments and the troposphere and the ionosphere, etc. And that's basically it. So I just wanted to go through Lucia's slides because I think she has these nice things where she shows what the relative magnitude of stuff is. So let's break for 20 minutes, and then after that, when we come back, we will start to play with some software.
Okay.
So about 3:45. but it's not working like I thought it was supposed to. And I can't get in touch with Sergey Boletin, who wrote the software. So my suggestion for the rest of the afternoon is open for questions. And then we'll return to this tomorrow after I've had a chance to investigate. NewSolve is a package that we use to do the initial analysis. And usually if you type NewSolve, you get this window, but then there are options to open sessions and do stuff with them. And I am not sure if I'm opening it in debug mode or demo mode or something, but it's not doing what I expect it to do. So, and you guys see exactly this, right? You don't see anything else? I mean,
might be something about the network because we are in another country.
it shouldn't be. It should be able to run just on the screen. And there's supposed to be this screen and then another screen that comes up. And I just don't see where the other screen is. Unless it's... Okay, so sorry about this. Let me ask, are there any questions we have from the rest of this, from earlier this afternoon or from last week?
About the presentation, when we need to present?
Are you ready?
Huh?
Are you ready?
No.
How about Wednesday? Presentation on Wednesday morning?
Wednesday morning.
Presentation for execute the codes.
Yeah.
Oh,
What language?
I can execute the codes.
Can you put Friday?
No.
I can execute the codes.
You can execute, NewSolve works for you?
Na
So
sexta a gente
we
vai.
not work. The
Vamos
last
resolver
try
o dia.
other thing.
Vamos tentar fazer um Zoom com o pessoal que estava online e com o pessoal da operação. Então, se for, sei lá, das 9 às 11, por exemplo, as apresentações.
Na sexta?
Se queria na sexta, é isso?
Porque pra mim foi melhor. Porque eu tô na semana de provas, mas sim, pode ser qualquer outro dia se for de tarde eu posso.
Quantos grupos tem?
2 eu acho, mas eu acho que o único que tá completo desde o início é o nosso.
So, excuse me, sorry. There's an online question that says, in which place the station coordinates are determined in the focus? And the answer is, most antennas have two axes, an axis that rotates like this, and another axis that rotates like this. So this is the elevation, then you have the azimuth. And these two axes actually have an intersection. Friday lunch, we want to have a pizza party to celebrate the end of the class.
Really?
Yes. So, so let's try to get all the work done before then.
So maybe you can remember to these people online But we plan to have a meeting 11,
Okay.
11, 12 on Friday.
Yeah, so everybody who is online, on this Friday, we plan to have a meeting from 11 to 12 to just review the course and to talk about future directions and any questions that people might have.
So we'll send the link,
Yeah, we'll send a link
a Zoom link.
as to participate.
Let's try install also.
The presentation, what you serve on, like a PowerPoint presentation and we talk about it? What do you want?
What do you want in the presentation? You guys are talking about EOP, right?
Yes.
How long can you talk?
Medium. I can put an artificial intelligence to talk if it's better. Because my English is medium. I don't know if I can do a presentation, a long presentation.
Deixa eu trazer o jeito que eu AI que eu tenho isso. Fala português.
Mas fala, mas é ao vivo e ela.
Já tem alguém no vídeo, também já colocou no vídeo.
So, give a presentation for half an hour. Is that too long?
I don't know. Let's see.
And then questions for like 15 minutes. Have you ever given a presentation before? Have you guys given presentations before?
So I just want one look.
Aqui só café com leite. No, I never do a presentation. It will be the first time.
In English.
No. Em português já fiz, né? Na fala.
You never did a presentation in English.
No, no.
How about in Portuguese?
Yes, in school.
And so, what did they tell you how to give a presentation?
Same thing.
So, usually the rule that people say in English is tell people 3 times. At the beginning, you say what you're going to tell them, and then you tell them, and then at the end, you remind them what you told them. So, I mean, that's just this one thing. Don't use a lot of equations.
But 50 slides for 30 minutes. 50 slides, 15.
Oh my God.
So something like, yeah, I mean, the rule of thumb is like, and different people have different things, but Jean-Pierre said 15 slides, or I say 30 slides, but not 100 slides.
The length for a TED presentation.
Não, mas tem que estar de uma hora, tá doido?
Você sabe uma vez?
É porque ele disse que não, ele acabou de falar que não dava pra fazer, porque vai ter um encontro. Ele falou que não dava. Ele falou que não dava sexta-feira porque vai ter o Zoom, né? E a festa da pizza.
É, mas o Zoom é 11h30 do dia.
Então,
Pois é, a tarde.
sim, no almoço, né?
No almoço, isso.
Comigo, eu prefiro sexta. Se dá mais tempo.
De 9 a 11. 10 a 11.
Porque a gente ainda tem que fazer os slides e apresentar. E ainda estou em semana própria. Mas tá certo. O senhor não me passou o e-mail com o material. O senhor falou que ia me passar um e-mail com o
É.
material.
Você tem que estar com a chave?
Com o que? Com o pendrive?
É.
Eu não. Tem pendrive. Eu lhe mandei o e-mail.
É, então, pois é.
Uhum.
Tem o e-mail?
Eu lhe mandei por WhatsApp.
Tá. Então,
Deixa eu mandar outra mensagem.
Professor, a question. How many people decide on those models? I suppose you assemble, how many people on those teams, and how do you decide about the model? How is the process of this deciding which model is the accurate one? How do you update the models?
So the first thing you have to do is you have to demonstrate that the new models are better in some way. And
Some way.
so, yes. So in VLBI, we have some set of tests that we do. And one of them is, are the new models more consistent with the data? And that so are the new models more consistent with the data? One of the things that we can do in VLBI is that we will have, every 3 years, we run a series of sessions for like 2 weeks where we observe the same network every day. And, we do this to sort of test the state of the art. And one of the things you can look at is, are the station positions consistent day to day? And if you put in a new model, do they become more consistent? So that's one of the things. And the reason you like to look at a short period is because if you look at a long period of time, there are seasonal effects that cause variations. So that if you compare a station, say, in May and in December, due to loading effects or something. Whereas if you could compare it on Monday and Tuesday, it should be pretty much the same. So another thing you can do is you can compare VLBI results with GPS results, or VLBI results with SLR results, and see if they're more consistent. I think I mentioned earlier that when you generate the terrestrial reference frame, you have 4 techniques that go into that. One is GPS, one is DORIS, one is SLR, and one is VLBI. And VLBI and SLR set the scale of the reference frame. And that, the other things are insensitive to if you just expand everything slightly. And for a long, long time, there was a disagreement between VLBI and SLR on the scale, and that one was positive and one was negative. And nobody knew where that was coming from, and it turned out that SLR recalibrated their instruments, and then they agreed with VLBI, or closer to it. So that's...
So, as VLBI was correct.
VLBI was correct in that instance, yeah. Yeah.
And consistency, by consistency you mean
I
repeatability?
do it.
You got it working?
I study Rousseau.
Okay.
Let's go.
By consistency you mean repeatability of the results?
Right, yes, the repeatability of the results. Or the other thing I mean is that if you look at
You just need
on an individual session,
open.
if the residuals are smaller. So you have like consistencies within a session and then across sessions. Within a session, then between tech. That you
Ah, remember my network. Loading. Continue. Close the camera. Share screen. Share screen 2. Allow. Okay, got it.
Okay. Let me show you where the manual is, so you can at least start looking at that. And I'll try to make a copy of this, upload a copy to.
Teacher, minimize the network, please.
Do what you want.
Mirror associate. Okay. Minimize. Okay, we solve past. No, we solve folder.
Do you see this path down here? SGP, VLBI, progs, new solve.
I find the folder in search.
Yeah, but I'm talking for the
Okay.
these guys back here.
Eu sou installing now. Ah, have you got it? Yes.
Oh crap.
Teacher, you excuse me. Okay. User guide.
So one suggestion I have is navigate to this thing. Do you see how I got there? No? Open, okay, so I'm going to open. Let me go. I don't know how to show the complete path here.
Other locations. In last option, computer.
Find SGP VLBI.
SGP VLBI, okay.
Then go to progs. And go to new solve. Go to share. New solve. Doc. So this gives is a bunch of user guides.
Quem não conseguiu é só me chamar com ajuda. Conseguiu?
Mas é qual dos manuais?
É o user guide, terceiro. installation. Ah, script is listen to change the folder file to installation. The folder file.
Anyway, I think that's it for me for today. I'm gonna go home and investigate what's happening here. So sorry for everybody online that I don't have anything more exciting for you.
Now is compiling the solving computer. So just need leave the computer and the computer is working.
Hello. Hi, Sergey. Thank you. No problem. So, when I type new solve, it comes up, but I don't have the option to open up any files or anything like that.
Pronto, deu erro no solve, aí eu usei aqui o tutorial que tem aqui no solve para instalar o solve. Eu acho que o solve do computador já deve ter terminado.
I'm looking at the user guide. So tell me how to, once I open up new solve, tell me what I need to do. Sure, I can do that in like an hour or so. I mean, I could try it. I'm not using a Linux machine, so I'm not quite sure how to do that. Let me think about that. Okay. 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 Never mind. I was able to figure out how to open up a something. Uh-huh. Okay. 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 Thanks. Okay. Yep. Yep. Mm-hmm. Okay. 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 Thanks.
Pode fechar assim no computador.
I will. Okay. So I'll see what I can do, and if necessary, then I'll call you back with Zoom or something. Yeah. 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 I understand. Okay. Thanks, Sergey. Yeah. Okay. Okay, everybody. I spoke to the guy who wrote the software, and once you have new solve opened, type Control O, and it should give you this thing here that lists all the sessions.
Ok. Ctrl O.
Can you repeat?
É Ctrl mais O.
Fazer mais bota no sol.
So do you see that?
Yes.
Now let's go to this 2022 directory. And here's a list of all the VLBI sessions for that year. So I'm going to go to 2022 April 04 EXA A.
Can you repeat the name of the?
Can you see that up there?
Okay.
Show. Rigos. Ok.
So if I look at this, I mean, this has a session. I can see it has Argo, Heart 15, Coque, Matera, Niallison, etc. I'm going to go down here and click on one of these files. Hopefully this will work.
22 lá.
I got to click on the version 4.
Ah, ele foi de forma aqui.
So do you guys, are you at this stage? So this is what we'll use tomorrow to process some sessions. But let's go to, click on this Stations tab. And this will give you a summary of information about the session. It gives me all the stations there, how many scans there were, how many observations, etc. That's if I go to stations list. Let me go to stations plots. How do I change this? Can I change the size of this thing? I want to.
Ok. Just a second. Let's try do it. No, the solve can't change the proportion. No. Minimize and exit. And the window can't minimize.
Okay. Well, let's see. If I look down at the bottom here, you can see it has time UTC as one of the axes, and then the other axis is, it says cable cal, but it has other options too. So one of the things I can do is hit met temperature. So this shows me what the temperature is at all the sites during this session. And on this axis over here, I can turn on or off sites. So I can turn them all off, and then I turn them all off by clicking that minus. I click on all of them by clicking that plus. I click them all off, then I can just focus on what I want. So this software was written by Sergey Bolotin, and it took him several years to use it, to write it. And when he wrote it, I said, I want to be able to see anything versus anything. So here I have temperature versus temperature, but maybe I want to do temperature versus pressure. And then you can see this sort of nice thing there. And I should be able to,
Select.
yeah, I should be able to change the scale, but I'm not quite sure how to do it. What else can I see? I can look at, let me go back to time to meet. Yeah, that's not what I want. Cable cow. What is it? Yeah,
Let's try to change the resolution.
that's what I wanted to do.
Let's try it. Screen, displays,
Resolution there.
displays. No, can't change.
Okay, okay.
Let's try this. Apply. Let's check the result. Tap it.
That's
No.
worse.
Displays. Yes, don't have a choice.
Okay, okay.
Display. Apply. Tap configuration. Resolve. Open again, teacher, please.
Anyway, so tomorrow what we're going to do is we're going to use NewSolve to process some sessions. And we'll process the session. One of the things we'll do is we'll process the session that just ran this last week.
Okay.
And that's basically it for today. So thanks for your patience. And I'm going to log off.